So like in the little clip I just showed you, Vector, the anti-superhero, I guess you could say, was talking about how he wanted to do crimes that had direction and magnitude. All right, so there are plenty of things out there that you have learned about that are just scalar. And these don't have direction. Like if you're on a scale, you weigh yourself in the morning. That doesn't have a direction, but it's got a magnitude. Okay, so however heavy you are, that is a magnitude without a direction. So that's called a scalar. Okay, there's a lot of examples of things, you know, like temperature. That's a number. Think of it as a number, but it doesn't have a direction. All right, so if things have magnitude and direction, then you can make a vector for them. Would you agree that this plane has a magnitude and it's going in a direction? Well, then you can make a vector for it. And typically you use an arrow, and that arrow goes in the direction that the vector is, and how long the arrow is indicates magnitude. Would you agree that the black arrow has a bigger magnitude than the blue arrow? Well, yeah, because it's got a longer length, and so therefore it's considered bigger. All right, so you got to figure out how the magnitude of vectors is one of your things that you have to learn how to do. But the main thing I'm trying to get across is if you've got a direction and a magnitude, then you're a vector. Now, are these two vectors equal? No, because one's got a different magnitude, but they were in the same direction. Now, if I could draw another blue arrow in the exact same direction, I'm trying to be exact same direction and exact same length, then this is one of the things that's hard to get used to. Those two blue arrows, if they're both going the same direction and they're both the same length, then they are equal. Even though they're not in the same place, they're equal. So you can move it around. Okay, the vector could be over here. As long as it's the same length and the same direction, then that's the same. So how do you get picky about like the same direction? Well, we say if it's going over, like let's say 4 and up 3, do you get it's the 3, 4, 5 triangle so I'm setting up there? Then this magnitude was 5, and it was going over 4 and up 3. Well, then I can do the same thing over here and say, well, this one was going over 4, and this one was going up 3. Then it's going to have a magnitude of 5, and it's in the same direction. Does that make sense to you? So these blue arrows are all equal. What if I made the blue arrow go exactly in the opposite direction and then put the tip there instead? Is that going in the same direction? Of course it's not, but it's got the same magnitude, and it's kind of similar. What you do is you put a negative on the vector, and then it'll be the same vector except going backwards. All right. So this is how you write a vector. You put an arrow over the top of it, and you say it's going from A to B, or you can just say this is vector A. It doesn't have to have 2 points on it. It can just be called vector A. And that AB with an absolute value around it, the absolute value is reminding you that the magnitude of the vector is never negative. So you can't say that the magnitude was negative, but I can do the opposite of a vector. If this is vector A, then I can throw a negative on it and say that's the opposite of vector A. And it's going exact opposite direction. And it's the same magnitude. So again, is the magnitude negative? No. But the vector can be. You can put a negative on a vector, and then you're saying same vector, but opposite direction. So the direction changes, not the magnitude. The magnitude didn't just get negative. When I said, I'm going to go that way, the magnitude stayed the same. But the direction is the opposite direction. That's what the negative means. Okay, what would a zero vector mean? That would mean that it's not going in any direction and wouldn't have any magnitude. Or it's something that has a magnitude but doesn't have any direction. So like for instance, let's say you had something that was 60 feet sorry, 60 feet long, but it wasn't moving at all. Now it's got a magnitude, but it's not moving, it's not going in any direction. Is that the 0 vector? No, that's a scalar. A scalar is something where it's like your weight. Remember, that was a scalar. What's a 0 vector then? If a weight with no direction is a scalar, yes?
A direction with no magnitude.
A direction with no magnitude would be, thank you, the 0 vector. It's a direction, but no magnitude. Like if I said, I want you to go that way, okay? And then you're like, how far do you want me to go that way? 0. Then you at least know the direction. So there's a place for this, but it's weird, no doubt. Okay, now. Which of the vectors have the same magnitude? So I would like you to decide and write down which ones you think they have the same magnitude for letter A. Go down here and answer the question. Now they're not like, oh, these 3. It's clusters, like this and this one are the same, and that one are the same. Take a second and actually write this down. I know some of you are doing that lazy thing where you're just kind of staring at it, thinking. Thinking is a good start, but take action. Engages a different part of your brain. You remember it better. Oscar, give me an example.
G and U.
G and U have the same magnitude, but they're going different directions. But they still have the same magnitude. Why? What's the magnitude about?
It's just the...
In this case, it's the length.
Yeah.
Okay? And I know it could mean something else. It could mean like how heavy the thing is. It could mean how fast the thing's going. It could mean a lot of different numbers. But if G and U both appear to be the same length as each other, then G and U can have the same magnitude. Give me another combo. Yes?
DNF.
I agree. DNF, the first ones that I saw that looked the same size. Do you think E might be the same as G? I don't know, do you have a way of measuring that on your iPads? Is there like a measuring tool? Is it built into Notability? Yes.
If you just draw a line and you make it like a sticker, then you can rotate it.
Oh, do it and tell me if they're the same.
Oh, which two?
Like E and G. I sense that they're the same, but I can't quite tell. So what he's going to do is something on his iPad where he can draw it, make a sticker out of it,
Yeah, they're the same.
and rotate it. Aha!
Along with A and B as well.
And A,
Oh no, E is the same as G and U. So
E, G, and U. Okay.
and A and B.
E and G and U. Okay. Okay, so remember, magnitude is about length. Are they the same exact vector? No, because you have to be the same direction and the same magnitude. Are there any of those where it's not just the same magnitude, it's the same direction, and therefore they are exactly the same? Yes?
E and B.
E and B, they appear to be going the same direction and they appear to be the same length, and you check that length thing, right? So then E and B are equal. They are the same exact vector. E and B are, and so are D and F. But you had that under the same magnitude. Yeah, they were the same magnitude. And they're the same direction. So they're equal. Okay, good enough. I think the rest of those questions are obvious. So if you're going to add a couple vectors, if I was going to add the A vector to the B vector, then I would just move one of them so that you can put tip to tail. Try to remember that. Tip to tail. It's like I slid this up right up there, and that's one of the disadvantages to the software I'm using. It can record me, but it can't like grab something and slide it. So you could on your Notability. And then This B is now up here. Remember, this B and this B are exactly the same because they're the same direction and the same length. And then the answer to the addition of the two vectors is a vector that goes from here to here. If you add the one vector to the other vector, then those two directions together add up to the red one. So effectively, it's like if you nudged a ball in the A direction, and then after the ball rolled for a while, you nudged it in the B direction with that same magnitude, then it would have been the same as if you'd have nudged it in the red direction right from the start. The ball would end up in the same place. And how far is that length? Well, do you remember a unit where we figured out, like, this is not a 90. If it was a 90, it'd be easy. I could do a squared plus b squared equals c squared, but it's not. So let's say that that's like 100 degrees. Do you remember a unit where if we knew this was 8, and 8 is the magnitude, the length of it, and we knew this was 9? Do you remember that formula that takes the 8 and the 9 and the 100, and it tells us how long that side is? Yes?
A squared plus b squared minus 2ab cosine c plus c squared.
Nice. That is the law of cosines. You might use that this chapter. You may want to write this down. A squared plus b squared. And it's not just equal to c squared. It will be eventually. What was that extra little factor? Challenge yourself to remember it. He just said it a second ago, but do you remember it? A squared plus b squared minus... Write it down. The act of challenging yourself to remember it increases the probabilities that you will remember it when I tell you. And maybe you already do. Raise your hand if you actually have a good enough short-term memory that you remember what he just said. Okay, or you weren't paying attention well enough. I'm going to say it one more time, see if you can retain it long enough to write it down. Minus 2ab cosine of a big C. And actually the C I wrote there was a little too big. It should use small c. Do you guys remember that the small c is the length of the side and the big C is the angle? A squared plus b squared minus 2ab cosine c. See why they call this law cosines? Make sense? Okay. All right. So another thing that's going to kind of blow your mind is when, we'll wait till we get to 3 dimensions. Right now we're not in 3 dimensions yet. But. Okay. So if I have two vectors, I have this little vector. I'm going to call it M. And this little vector, actually I can make it a lot different size, like that little vector. And I'm going to call it R. Mr. MR, I'd like you to show me what that means. Tried to make it neither of them like parallel to, like just be straight, so to speak. I'd like you to try to put them together and see what MR as a vector is. The M plus the R. M is a vector plus R is a vector. What does that look like? Now some of your minds went here and you moved the M vector over and did this. And you tried to keep it the same direction and the same magnitude. And that totally works. Do you get that the answer would be the red one? That's got a weird name. Write it down so you remember it. It's called the resultant. It's not just the result. It's called the resultant. Now, could I have added R and M the other way? Yeah. I could have made the R vector, which was this, and I'd like you to note that those two resultants, the red ones, are they the same length? And are they in the same direction? And therefore those two resultants are the same. They're considered equal. But one's over on the left and one's on the right. They're the same though. That's the thing you got to get used to in vector world. Just because one's over here and one's over there, they're the same. They're equal. Okay. If they have the same what and what? Direction and magnitude. That's what vectors always come down to. Okay, so I'd like you to just practice that. Would you please make, let's do this one. Make A plus B. You have to draw it. Do whatever you can to make them exactly the same. So if you want to use that little idea of, tell me one more time for the people at home that are using their iPads. How did you do it again? You made a sticky?
Oh, so you like, so if you had 2 lines, you saved them, like you grouped them, and then you can rotate them as like a box.
Okay, so like on the iPad, they've drawn a line over this one. Is that what you're saying?
Yeah.
Okay, and then you do what?
Use the scissor tool,
Use the scissor tool.
and then you, when the black options come up, you press group, and then you can rotate it.
When the options come up, you press group, and then you'll be able to rotate it. Okay, now I want to probably not rotate it. I'd want to just move it over. And so I'm going to move it over like here. Oh, I just changed its angle. That's one of the things that would be nice about being able to just slide it around. There, I'm trying to say that that red one is the exact same as the red one. And this blue one. If I do this, you've missed the point. It can't, that doesn't give me anything. That's not it. Okay? That would be tail to tail. You don't want it to go that way. You want it to go tip to tail. So I can do either tip to either tail, but there, that's my best attempt at A plus B. Could you have done it another way? Yes, but the cool part is this black resultant. I just kind of messed that up. I'm going to try again. There. The resultant should be at the same exact angle had you added B plus A or A plus B, and it would be the same length. And how long would it be? Once again, this would be a triangle problem where you know a couple of the sides, and you'd have to know an angle, but then you'd be able to figure out the other side. Is there another formula besides the law of cosines that could come in handy for not right triangles? If it's a right triangle, it's easy. A squared plus B squared equals C squared. Yes.
Law of sine.
Which is?
Sine A over A equals sine B over B, which equals sine C over C.
And that's good for when you have a triangle, because these will always form triangles. It's like, well, this one's, tip, and this one's tail to then makes this red one, which would be the resultant. You always got 3 sides, and you can call one of them A, one of them B, one of them C. And when it's a law of sines, you just need an angle and the side across from them. So like if I knew this combo, and you always need to know 3 pieces of info. Okay, so just one angle and one side across wouldn't be enough. But if I knew three pieces of info, I could figure out the 4th. Now, if that could be one more angle, or maybe I need to know one more side, but just one side and one angle across from each other is a good start, but you need one more thing. Okay, so there's just some reminders of stuff you're supposed to know from the past, plus a whole bunch of new vocabulary for adding vectors. So if I had to add these 2 vectors, I'm going to try to do it a little faster. I'd say, there's A, and I'd say, maybe I should label it, and there's B, and I put them tip to tail, and then I go, the green one here is called the, what again? Resultant. And it's what the other one would result to. I still like the idea of you're rolling a ball in this direction. And then if you nudge the ball with this amount of force in that direction, it would end up here. And it would have been like if you had put those same 2 forces on it from the beginning, it would be the green one. The ball would still go to the same spot. It would just kind of take the shortcut. Okay. So that's kind of like you have 2 ropes on the safe. This problem is ahead of its time. Of course, we've always imagined robots, but Elon Musk says that his company thinks they will be actually mass producing at small scale robots next year. They aren't going to look exactly like that. He's already said what they kind of are going to look like. And holy cow, it's actually happening. I don't think they're going to be able to do much at first. Like, seriously. Like, they might have programmed them to dance or something, you know, kind of like you've seen before on Boston Dynamics robots. But then as the programming gets better, they'll be able to just over-the-air update it through Wi-Fi. And poof, he's got a new program, and now he can do dishes. Poof, he's got a new program, and now he can, I don't know, pull on things with a rope, like this is. Maybe you can get you against two of these things playing tug of war in your backyard. Who knows? They'll probably keep on launching more and more things that the robot can do with software. And if it's got 10 fingers and 10 toes and maybe it doesn't have toes. I don't know, actually. Maybe you don't need them that much. Interesting thought. Anyway, and eventually then they can program them to do a lot of things. Like they could program it to type, couldn't they? Pretty soon, it's just kind of fascinating for me of what that could turn into. All right, so this is a pulling force, so it's a force in that direction. And this is a pulling force, so it's a force in that direction. Which way is the safe gonna go? Can you picture it in your mind if they're both pulling on it? And let's imagine that it's on ice or something, so it actually can slide. Because otherwise you might be like, it isn't going anywhere, that's really heavy. Would you agree that the safe is gonna go kind of in between these two, in that way? Does that make sense to you? And what would that have been like? Well, that would have been like, I take this one, I'm going to call this A, and I move it up here. And then I've got tip to tail, right? And aren't this A and this A the same? Yeah, so then that's the resultant, and that's the direction the safe would have gone. That kind of makes sense to you? No, this isn't perfect. I am not drawing them to scale and everything, but. All right, so you can do vectors to make a real world situation. All right, that's it. You've made it to the end of Vectors Day 1. I also need to give you tests back from last hour and stuff. So this is the actual assignment, and more than ever, because today was really pretty short, I want you to do a bunch of these problems in class without my help, but maybe checking with the kid next to you. So I'm going to give you some time, and then I'm going to ask you to check with the kid next to you. And all this part here is classify it as a scalar or a vector. Let's do the first one. A classroom chair is moved from the front to the back. Does that have a direction? Yeah. Would there be something about it that you could quantify with a number, like the weight of the chair? Yeah. The speed you move the chair at. Yep. So I call this one a vector. The balance in a bank account. It's just a number, isn't it? So what's that? A scalar. All right, I'd like you to think through the rest of them, whether they're vectors or scalars. And then you have some problems here where you're going to actually strongly recommend you actually draw them like we were doing before. Don't try to just do this in your head. Draw the picture out. I want to do one of these with you so you can understand, you know, kind of what they look like. And I need you to understand this language of absolute value kind of thing. So let's just go to this page together. You can finish that other page later. Those are easy. Okay, so look at number 5. AB plus BC. Well, right away I'm going AB's like this, BC's like that, tip to tail. They're already tip to tail. Cool. Then that black one, that is it. That is the single vector and I'm trying to copy it and keep it the same length. There. That's your answer. And it's what, though? What do I name it? Your answer isn't a drawing. Your answer is a letter. AC. And these should all have little tiny vectors on top. And before, I don't know if you ever noticed that these are like half of an arrow tip. Just to clarify, that is an old geometry term that meant ray AB. Here's how these are supposed to look. You might think that that's the same thing, but it's not. That's a vector. They do that on purpose because an arrow tip has already got a definition. That meant ray. That is how you're supposed to write it. Okay, so there's my final answer, AC with a half arrow on the top of it. Why is it AC? Because look, it goes from A to C, and it's a vector. When you're drawing them, you put tips on both sides, but when you're like writing the answers, you put a little half arrow. So would you please do that on all of these? It's kind of fun once you get used to it. There. Okay, I think you got the idea there. And what does this mean again? Well, that means magnitude. Of A. When you put the little bars around it, you're saying the magnitude is like how big it is. Now, they aren't asking you how big is it. They're actually asking you, is the magnitude of A the same as the magnitude of B? And take a look at them. Can you tell that little a and little b are not the same magnitude? They're not the same magnitude at all, because b is way bigger, because it's longer. Okay? So a and b are not equal. False. Okay, now I think you know everything that you'll need to know. Continue, and that's all I have for the video for today.